So let me start with some disclaimers. First one is that there are no experiments or simulations in this talk, so I'm by training a pure mathematician. I'll talk to you about something that I'm struggling with. It's not something where I have, it's not that I'm going to come to you now and present you with the theory of deep learning and you should forget everything else you heard about it. One of the reasons I'm giving this talk, and I think it might be interesting for me to give it to a broad audience, is that I'm happy to get some feedback. Let me start from this perspective. So, as probably most of you know, deep nets mix linear and nonlinear functions. And one question that one may want to ask is, why is nonlinearity needed? Of course, there are very simple answers to why is nonlinearity needed. If you compose linear functions, you get a linear function. I'm asking maybe in a different perspective, why is it that nonlinearity needed? And what I want to start with today is just to give you, my take on this problem, is maybe to give you the simplest in question mark, most natural in question mark, data generative model that requires nonlinearity in order to do estimation. And then I'm going to talk about more realistic extension. I mean, the basic mathematical models, as somebody who is again trained in pure math, I want to start with the simplest possible model where I can explain and I can prove that nonlinearity is needed. And once I do that, I want to say, okay, how is this related to the data generative processes that we see in data that deep learning is learning? And there are many answers to that. So for those of you to this question, and for those of you who know the literature of the mathematics of deep learning, there's a lot of work going back from the 70s about the expressive power of deep learning, which functions you can express. So you can express a lot of functions, even with one layer of deep nets. But this has to be exponential width. So there's a lot of back and forth about this question. For me, this is maybe not so interesting because the answer is that indeed, with one layer of deep net, you can approximate any function. This is from the approximation theory perspective. And then the question is, if you can express so many things with one layer or with multiple layers, even if it's not very wide, if these functions are hard to learn computationally, maybe this doesn't mean so much. So what I really want to do is I want to come up with simple, natural, maybe interpretable models of generating data that may be similar, maybe have some of the features of the data that we're seeing that require to do something like deep nets. So that's the goal of this line of research, which I'm carrying over mostly on my own in the last couple of years. So I'm going to tell you about a very simple process that will require this nonlinearity. Okay, so this is the very simple process. It's a process that I didn't invent. It's a process that I'll mention in a little bit. It studies some ways since the 1920s. It's the Ising model on the tree. One interpretation of that. So here's the interpretation that I'm going to give you. There's going to be a process on the tree. There's going to be some finite set of colors. There are going to be q possible colors. When I say color, they would randomly, I mean uniform at random from the q possible colors. Then I'm going to repeat the following process. For each child of each node, I'm going to look at the parent of that node, and I'm going to copy the color with probability theta. Theta is some positive probability. Otherwise, if I'm not copying, I'm going to toss a coin or roll a die, and I'm going to choose one of the other colors uniformly at random. So that's my process. So maybe my theta here is pretty large, maybe it's 3/4 or something, so I mostly copy. But once in a while, I will, decide to re-randomize, and maybe I re-randomized here and here. When I re-randomize here, I got the same color, which is red. When I re-randomize here, I got the colors that is blue. And so that's the process. It's going down the tree. All of the coin tosses, all of the rolls of the dice are independent. And somehow, in terms of the formulation of the results, and also in terms of the mathematics of thinking about it, it's better to think about this model than the model where you actually flip to a different color. But of course, they're equivalent. There's just a change of parameter that tells you how one relates to the other. Given the leaves, so given I know the structure of the tree, I see the colors of all the leaves, I want to say something about the color of the root, can I do something better than random? So the answer for every finite tree is yes. We're not interested in finite trees, we're going to be interested in the limiting process. Is the information preserved as the tree is getting bigger and bigger? That's the question. Okay, so for the mathematicians among us, here's the definition. I think everybody understands the intuitive picture. So given the leaves, can we guess the color of the root? So the mathematical definition, which I'm going to write here, and this is one way of saying it, we say that the reconstruction problem is solvable if this limit is greater than 0. So what is this limit? First of all, in order to simplify things, my trees are going to be very simple. All of the nodes are either going to be leaves or they're going to have exactly b children. Okay, I'm not going to have trees like the trees that I had before, just to simplify the discussion, that's what I'm going to have. And the assumption is the tree is very, very big or infinite if you're a mathematician. And what we're interested in the statistical distance. This norm represents the statistical distance, or the L1 distance, between the probability distribution on level L. L is a very large level, given that the root of the tree started with the color A, versus level L, given that the root of the tree started from the color B. I want to know, is there some residual information as I go down farther and farther down the tree? It's clear that you just lose information, but maybe the amount of information that you lose is bounded at some spot and you don't lose anymore. If you want to think about it, computation, maybe I have a project that I want humanity to know for forever. If today I toss my coin and it's heads or tails, and I come to some hardware company and I tell them, build me this circuit that will remember this bit forever. And my design is that just duplicate and duplicate. I know that there are going to be errors. I'm going to duplicate and duplicate over and over again. And I want that in a billion years when people are going to look at these bits, they will know my value of my coin toss. Okay, this is a ridiculous question, but that's how you can think that this is a primitive in the business of remembering in noisy circuits. Right? So that's one interpretation. A much more natural interpretation. This is actually one of the places where we will be going. This is a model of genetic inheritance or evolution. Because our DNA sequences, or species DNA sequences, go through a process a little bit like the process I described. So that's very natural to look at it. People in biology looked at it since the 70s, in biology and statistics. Okay, now there's the big physics picture and a little bit of computer science picture. So let me start with the computer science picture. So if your algorithmic task is given the colors of the leaves to compute compute the posterior probability at the node, this is a very easy algorithmic task. You run what's called belief propagation or dynamic programming. It's a very efficient algorithm. It's very easy to run. If you analyze the typical behavior of how belief propagation is behaving, what you're doing is you're doing replica calculation in statistical physics. So you may have not known that, but these two things are exactly the same. And somehow the question if this algorithm finds a non-trivial answer or not is closely related to questions about replica symmetry breaking. Okay, so if you've ever heard about the theory of diluted spin glass, somehow this process plays a very, very central role in this theory. And my goal is to show you this model is the model. I told you this is the simplest model that will require nonlinearity. So I'm going to start with this model. If there's anything you take from this talk is that there's this very, very simple model where doing something non-linear, truly non-linear, which is belief propagation, is much better than doing something linear. This is this model. How is this related to deep nets? Depending on how much time I have, I will try to approach how it's this related to deep nets. Okay, so here's the phase transition for Q equal 2. Q equal 2 just means that I have two colors, 0 or 1, or plus and minus. Each node has B children. Again, the copying probability is theta, otherwise I randomize. And delta greater than 0 means that the reconstruction problem is solvable, meaning asymptotically I can reconstruct better than random. I'm just reminding you what we were talking about. So here's the reconstruction threshold for Q equal to 2 and the BRE3. BRE3 means everybody has B children. The reconstruction problem is solvable. We know the exact threshold if and only if B theta squared is bigger than 1. So we know the exact threshold. We know what it is. And moreover, what's nice about this problem is that in the case of Q equal 2, which is like Ising model, just two spins, you can actually get all the way to the threshold just using linear statistics. You give me all of this data, billion years from now, I look at all of these leaves that I, paid a lot of money to remember, and then you ask me, what is your sophisticated algorithm for reconstructing? I said, I'm just going to count how many pluses and how many minuses there are. If there are more pluses than minuses, I'm going to say plus. If there are more minuses than pluses, I'm going to say minus. Thank you very much. This gets all the way to the threshold. Okay, so this is a very simple algorithm. It's linear. I promise you non-linearity is definitely something that's very, very linear, and the answer, the story here is very, very simple. We're good? Okay. Multiple proofs. I mean, this model was studied since the 70s in statistical physics. These are some of the names that were involved. The first paper is this paper by Blecher, who is Zagrebno from the 90s, and it's related to this Salas phase transition. A lot of interesting statistical physics. I won't really tell you too much about it. Okay, so this is Q equal 2, and as you feel, the interesting story will happen for large Q. But first of all, what we're going to generalize, and this is a result from about 10 or 15 years, maybe 10 years ago, we're going to generalize the previous result. We're going to look at large Q, instead of 2 spins, just plus and minus, I have any number of spins. Maybe I have a Potts model with 4 spins, or Q is the number of colors that I have. And it turns out that the safe threshold, b theta square is equal to 1. So if b theta square is greater than 1, then you can reconstruct based on linear statistics. If b theta square is less than 1, you cannot reconstruct based on linear statistics. So if you're just going to count or do some smart counting, now we have multiple colors. So maybe your statistics is, oh, I'm going to take 2 times number de blue minus 5 times number de red, and I'm going to look if it's in this set or that set. That's what's going to determine what you're going to do. So that is exactly the threshold for this kind of, all of these algorithms. And in fact, we know something much more general. In this joint work with Yuval Perez, we show that if the data that I'm giving is, instead of all the colors and where they sit on the trees, just the number of colors, the information that I'm giving you is not where they sit on the tree, just telling you, there are so many yellow, there are so many blue, there are so many reds, so there are so many green, tell me what's the color, then of the root, then the threshold is exactly the same threshold that we had before. The difference between this and the original problem, in the original problem I know where each guy is sitting, so I know this is red and I know his brother or sister is also red, so maybe I can use these correlations. And it's also the threshold for something called robust reconstruction, okay, which I won't really define. So far, very boring. Everything is linear statistics, and I promised you something nonlinear. So here's the non-linear. So this is what we said for linear statistics. This is the threshold, and something that I proved very long ago. It's not very hard, and it's been improved since. That for large enough Q, in fact, there is a regime of parameter where if b theta is greater than 1, that it's enough to reconstruct the root. Somehow there's an, okay, so let's look at these 2 thresholds. Sorry, maybe I should have written it in a different way. If b is bigger than 1 over theta squared, if theta is bigger than 1 over square root of b, then you can reconstruct using linear statistics. And if theta is bigger than 1 over b, which is a smaller number, a much smaller number, then you can reconstruct in some other ways, in particular using this mysterious belief propagation. Okay, so what's the conclusion of this picture? The conclusion of this picture is for this very simple model, it's just on a tree, I didn't have to write any complicated Hamiltonian, I could have, but I just tell you, oh, I just copy this probability and so on and so forth. For this very simple model, there is something interesting going on, that non-linear estimators, or sometimes some are doing something much better than linear estimators. And I want to mention that even though this is not proven anywhere, I mean, it's not about regularizing, or you can do all the tricks that you do for linear problems in order to get rid of. It's not about that. There's something deeper going on here. It's really not a linear phenomenon. If you want to reconstruct the root of this situation, you have to do something which you may call deep, you may call recursive, you may call something, but it's not just some linear operation on your signals, even modulus some regularization. So hang on, you promised to talk about deep nets. Well, the deep nets, or anything to do with real data, what's going on, you're telling us all this story, what does it have to do? I see some skeptical faces, I'm also skeptical, but let's go a little bit towards other models that might be of interest. At least let's try to do the following thing, let's try to reconstruct some kind of network. Right? Deep nets are some kind of network. Here it was about reconstructing one specific value. Let's think about reconstructing a network. So here's a problem I like a lot because it's trees. I hate networks. Networks are a pain in the, but trees are very nice. You can do with trees whatever you want. So in fact, this is the problem that I mentioned before, the problem from biology, phylogenetic reconstruction. So you want to reconstruct a tree T. Let me explain what is this tree T. So in biology, this is B equal to, not D equal to, it's the same as before. The trees are all binaries. This means, again, every node has either 2 children or 0 children. Why does it make sense in biology? Either there's bifurcation, there's one species and then there's a big earthquake and, part of them go over here and part of them go over there and, it becomes these 2 different species. Or, it's the same species and it stays together. What is this data that is used in order to reconstruct the tree? So it's going to be a sequence of colors at the leaves. So let me explain what that means. The sequence of colors are obviously DNA sequences or something like that. So sequence of colors means that each letter, so we're going to have a sequence of colors. So letter number 1, if we look at all the nodes of the tree, is going to be generated from the process I described before. Letter number 2 is also going to be generated from the process I described before. Letter number 3 is also going to be generated from the process I described before, each time independently. Most classical example is that the alphabet Q is of size 4, and the colors are A, C, G, and T. So what does it mean? Let's try to, or maybe the picture in the following page, which unfortunately I don't have a whiteboard, so let's just really concentrate on this picture here on the right. Okay, so we all focus on this picture on the right. I won't zoom in, but this would give you, there's a table of data here that's very important. So if I look at the first row of this table of data, what you have here is you have a sample of the process we described before with 4 colors, but only at the leaves of the tree. You don't see the inside of the tree, you just see the leaves of the tree, and you also don't know the structure of the tree. If you look at the second row, this is an independent sample from the same process. If you look at the third row, this is another independent sample from the first process, from the same process, and so on and so forth. What is the biological meaning of this, if you want? If you look at the first column, this is the DNA sequence of the species that sits in this node. If you look at the second column, this is the DNA sequence of the species that sits in that node, and so on and so forth. So you have this table of data. It's a little confusing. Probably took me a few months to really digest, so you will do it in 40 seconds. Okay? So you have this table of data. In this table of data, you have the following. Each column is a DNA sequence. Each row, meaning one specific position of the DNA sequence, looked over all possible species, is generated from the tree process that I described before. And what is the goal now? The goal now is different. The goal is from these sequences to reconstruct a network, which is a tree in our case, which tells us who is related to whom. So maybe these two guys have a common parent, and then these guys are cousins, and so on and so forth. So here's a picture that was drawn by one of my collaborators on this, Kostas Daskalakis. I really like this picture, because it helps understand what's going on. It just to repeat, the two perspectives. So one perspective, this is the DNA sequence of the species. Okay, obviously the species do not look like that. These are not dinosaurs and so on and so forth. But you can think about it as the following process. The DNA sequence of the species, just think about it as a binary string, which is the picture of the species. Then there's this noisy process. Then I go from this guy to this guy and this guy. These are 2 independent samples. Then you draw 2 independent samples. Then for each child you draw 2 independent samples. Then you get this noisy version at the bottom. What did we say? We say if it's actually binary, one thing that you can do, if you know the structure of the tree, you know that this dinosaur is a sister species of this dinosaur, and this dinosaur is a sister species of this dinosaur, all of them, or even you don't know in the binary case, you can say, oh, I'm looking at all the data at the bottom, and from all the data at the bottom, let me try to estimate the root. I'm going to estimate the root, and it's not actually going to be like the root, but the mutual information is going to stay positive. So that's the first problem that we talked about. This is the construction of the root, given the leaves. The second problem, the one that I'm mentioning, we're talking about right now, is phylogenetic reconstruction or recovery. So here I'm given all of these 8 species, and my goal is to say what is the structure of the tree. So I actually do not know when I get the sequences that these 2 species are sisters. And I do not know that these 2 species are sisters, I just get these 8 DNA sequences, and I want to know what is the evolution. What does the evolution mean? What is the tree structure that determines how they're related? So these are 2 different questions. One, I know the structure of the tree. So maybe you're confused. What does the structure of the tree mean? There's 8 leaves, everybody has a father, or a parent, everybody has a parent. But it is important that this species has a name. I don't know what are the names of dinosaurs. I'm actually not much into dinosaurs, but this species has a name. This species has a name. This species has a name. And it's really important for me to know if species that has name A is a brother of species B, or a cousin of species B, or a father cousin of species B. So I actually want to reconstruct the relationship, which is the tree structure with these guys having names. I lost some of you, okay? And the third question I'm going to talk about is semi-supervised learning, which may be more natural to you, so I'm just not going to define it. I'm just going to draw the picture, which I drew yesterday on the plane. This is the semi-supervised learning picture. So, of course, this is also a cartoon, but here is my generating process. There's some species here, which is the common species of cat and dog. Here is my first dog in the tree of species. Here is the first cat in my tree of species. And then I get a lot of data. The data, I don't know if you see, are all these DNA sequences. And now I want to open a lab that you will send me a DNA sequence, and I will tell you if it's a cat or a dog. Of course, in practice, this is super easy. Let's forget about, because cats and dogs are very different. Let's think about it abstractly. So what does it mean? It means that I'm going to have some labeled data and some unlabeled data. So the question marks means I have unlabeled data, and the non-question mark means I have labeled data. So what does it mean to have labeled data? It means that some biologist went to the field, collected DNA sequence, took a photo, and said, this is a dog. Okay, so we know that this is a dog. If this DNA sequence is a dog, this DNA sequence is a dog, this DNA sequence, and so on and so forth. But for others, we don't know. Now somebody is sending us some DNA sequences, one DNA sequences, or many DNA sequences, and tells us, please tell us if it's a dog or a cat. Okay, so that's the semi-supervised learning problem. I'm giving some labeled data and some unlabeled data. Like in the actual applications of deep learning, this doesn't have to be the picture. The amount of labeled data that we need is much, much smaller than the amount of unlabeled data. Okay, so there's labeled data, there's unlabeled data, and our goal is we don't care about the tree in principle. What we want to do is we want to say what is the label of the unlabeled data. What are the labels of the unlabeled data? Okay, so here is some result that I derived after some work from the previous results. You will see the connection. And somehow what will correspond to linear estimators is what I'm going to call shallow algorithms. So let's B, if you remember in our context, is 2. So the threshold B theta squared bigger than 1 is going to become 2 theta squared bigger than 1. And I didn't write exactly what is the setup of the semi-supervised settings. We need to make some assumptions, which I'm not going to say explicitly. But under some natural assumptions of the semi-supervised setting, you can deduce from the result that we've seen before the following. I forgot some parameters. I didn't tell you what is the sequence length. Good. So the sequence length is not too big. The sequence length is proportional to the depth of the tree. Okay, this is important for this result. Or at least that. So suppose that 2 theta squared is bigger than 1, then for all Q there's an algorithm that labels all the labeled data correctly. Moreover, this algorithm is shallow. I'll explain what shallow is in a second. And on the other hand, suppose 2 theta squared is less than 1, then it is information theoretically impossible for shallow algorithms to label more than half of the data correctly, between the cats and the dogs. So some of the same threshold that we've seen before is the threshold for something that I'm going to call shallow algorithm. So what is going to be deep algorithm? Deep algorithm is going to be an algorithm that's not shallow. So I need to define either shallow or deep. I'm going to define shallow, and deep is just going to be the complement. Okay? And the informal definition of a shallow algorithm is a shallow algorithm is an algorithm that cannot use the correlation between different features of the labeled data. Okay? That's the informal definition. Okay? Questions? Okay, and I can use all the unlabeled data. So I do have a slide here for, this is the actual definition of what is a shallow algorithm. Anybody want to stare at it? Take a photo? Okay, so shallow algorithm, there's unlabeled data and the labeled data. So what is the input to the shallow algorithm? You get all the unlabeled data. I'm giving you all of the DNA sequences. For the labeled data, I'm just giving you some statistics of the labeled data. I'm telling you, among the dogs, if you look at the first letter, 60% are A, 10% are B, and so on and so forth. The second letter is this distribution. The third letter is this distribution. I'm not giving you too high-dimensional joint statistics. Just very, very low-dimensional statistics about the dogs and the cats. So this is the formal definition. I just put it over there. Okay, so we understand shallow algorithms. So what about deep algorithms? Surprise, surprise. So the same phenomena that we've seen before, that deep algorithm outperforms shallow algorithm, doesn't just happen for this problem of reconstruction of the root, it also happens for the problem of reconstruction of the tree. So we said before, if 2 theta squared is less than 1, then it's information theoretically to label more than random, essentially. And if 2 theta is bigger than 1, and if Q is large enough, then it is possible to label all the unlabeled data. So what is happening here? There's an interval of the parameters where we can prove, it has nothing to do with the algorithm. We can prove that shallow algorithms, no matter which shallow algorithm you're using, you're not going to do better than random. You're just going to fail in labeling the unlabeled data. And in this interval, there are algorithms that are not shallow, and therefore I will call them deep. And these deep algorithms can label all the data correctly. This is a theorem for this model. It is, Here I give you an algorithm, it's an efficient algorithm, I prove that it works, it's completely done. And in the lower bound, it's really a lower bound. It says no matter how you use this information, you cannot do better than random. Okay, so we have this very, very simple model of generating data. It's essentially the phylogenetic model. We look at the semi-supervised setting. We see that there's some separation between deep and shallow. Okay, and now you want to say, okay, same question, what does it have to do with deep learning? And somehow my motivation for taking this point of view, I won't have time to tell you too much about the math, is somehow deep nets are used in biological context. So this is an example. There's this app by Microsoft that's called Fetch. This is not trees. Of course, breeds of dogs is a more complicated thing than just trees. You take a photo of your dog, it tells you the percentage of different breeds. It's very cute. And then, when I thought about it, I said, well, I know if an older guy used to ask questions like that, which is Darwin, obviously. And then I know of some biology that also tries to do the same thing, but this is from DNA sequences. And somehow the question that, what I'm trying to do is I'm trying to find sort of a common framework for what I call generative hierarchical models that includes both the biological models and something like maybe images of dogs. Okay, so I'll give you an example of the kind of models that I'm trying to study. And I think then I'll just take questions because I have much more stuff, but I won't tell you about proofs and so on. It's so late in the day. Okay, so this is the phylogenetic model. The phylogenetic model, what did we have? We have a DNA sequence at each place. And the DNA sequence, sorry, I forgot this guy, they also have DNA sequences. They evolved according to this process that I described. If you look at it in more detail, this is what we said that's happening between one DNA sequence to another DNA sequence. You mostly copy. This is copied, this is copied, this is copied, this is copied. Once in a while, you randomize and even randomize and flip, and you get a different letter and so on and so forth. So that's the evolution from this guy to this guy. This evolution, and the thing that, it doesn't capture, doesn't really, well, it's different from deep nets. In deep nets, both when you run it forward and backwards, there's correlation between features. So let's try to add something that has correlation between features. I'm going to look at the following model. It's discrete. So sorry, I know most of you are continuous people. I like these discrete spin systems better. So it's a discrete model. I'm just going to describe what happens in one edge of this process. When I go from one guy to the next, what will happen? So I'm going to do exactly the same thing that I did before. I'm going to copy, maybe it's a different alphabet right now. I'm going to copy this probability theta and randomize with some other probability. But then I actually want to mix things over. So how do I mix things over? I define a convolution. What is a discrete convolution? A discrete convolution is a general function of these t inputs to these two outputs. Take the t input, two inputs, you apply a general function on them, you get the two outputs. This mixes the two guys together, you get two mixed guys, and you do it over and over again. Of course, you don't do it, I should say, for those of you who know convolutional nets, that I don't do it with the same two guys. In the next level, I'm going to mix this guy and this guy, the first and the third, and the second and the fourth, and so on and so forth, because I want to mix sort of higher and higher features of my convolutional net. So that's the kind of model that you want to have. So this model already looks, it's a discrete version, but already looks quite a bit like a forward run of deep nets. And what I want to tell you is the same results hold for this model. Okay, so the same result that I told you about the phylogenetic tree also hold for this model. You have to do what you have to do, and I won't tell you what is it that you have to do. You have to do what you have to do, but the same result hold for this model. And again, to me, it gives you a separation between deep and shallow learning for data that is generated in a somewhat natural way. One of the things that I'm unhappy about is that, and for those of you who are mathematically inclined or have some interesting idea, this mixing of features should make the separation much stronger. So my conjecture, which is written somewhere in some slides but I won't show you, is that in fact, it's not a separation between theta equal 1 over square root of 2 and theta equal a half. I think that in these methods, even when theta is very close to 1, in particular exponentially close to 1 as a function of the depth of the network, you cannot reconstruct or solve the semi-supervised learning if you just use shallow algorithms. Right? So that's one of the reasons I'm not 100% happy with these results, is that I think that somehow mixing the features should result in much stronger results, and at the moment I cannot do it. Ongoing work, I could try to convince some people, including Anchor, to work on more realistic models on generating the data, in particular, not discrete. It's clear that things like images and speech, there has to be some continuous random variables in the background, so we're thinking about that. And we also have some more theoretical studies on how generative hierarchical model retain a bit of information if it's not just trees. And I'm going to stop.